In this mini lecture of the series Soil Slopes and Streams, we'll talk about soil creep and downslope transport. We'll focus on how processes that are driven by plants, animals, water, and ice can transport soil downhill and, in turn, influence the shape of the landscape. Eventually, we'll have a process-based answer to the question, why are hills round? We use these two terms in a different talk about hill-slope form. Two different types of systems described by the balance between their capacity for weathering and capacity for erosion. Which of the terms is best suited to the landscape seen in the photo at left? In weathering-limited systems, the erosion capacity exceeds the landscape's capability to produce soils. This may be because erosion is very fast, or because weathering and soil production are just too slow, for example, in an arid desert environment. This results in little to no soil cover. In a transport-limited system, weathering capacity exceeds erosion, such that there's a mantle of weathered soil at the surface that's produced more rapidly or as rapidly as it can be eroded. This is the system in which I'll set our stage here. Let's go to a soil-mantled hill slope to talk about how soils are produced and eroded. One important process of erosion and soil transport is known as creep. This is the slow downslope movement of soil by gravity. Creep processes are fastest at the surface and slower at depth. We can observe the impact of this process in the trunks of the trees. As the soils move, because the velocity is most rapid at the surface, the trees have to constantly readjust, resulting in the bends we see here as they grow vertically, but the soil attempts to rotate them. While creep may try to run those trees over, trees can also drive creep on their own. This is a process called tree throw, and let's focus in on this tree right here. It's rooting into the soil and maybe even rock at depth. When the tree falls over, maybe because it's dead or damaged, its root ball can rip up the surrounding soil and chunks of rock. This is a form of heave, heaving the soil away from the slope surface, such as we see in this blue arrow, and then falling back to the ground surface under the role of gravity. Heave is a type of soil creep. As the tree decomposes, the soil then fully falls back down to the surface, and this can result in a pit and mound topography. Imagine a bunch of trees falling over during their life cycle across this slope. This process can fundamentally change and erode the landscape, even though it may occur by isolated trees. In this system, you can see multiple trees that have fallen over and at least get a hint for that pit and mound topography. Frost heave is a process that results in transportation of sediment through ice crystal growth. Here we're looking at a soil in Vermont where needle ice has grown up perpendicular to the surface. This needle ice has displaced the soil near the surface. When that ice melts, once again, that surface will contract. Over time, this heave process will displace and contract soil until it moves down slope steadily. One of my favorite processes of heave and creep occurs by bioturbation. Gophers and other charismatic megafauna who bioturbate the ground contribute to movement of soil by disruption at the surface. And rather than occurring solely at the surface, it also occurs within the soil profile itself. Here we see a picture of a gopher who's digging its hole, and as it digs, it brings that mineral material at depth up to the surface. If this occurs on a slope, then we have that displacement down slope. Here, you can picture the imprint of this via multiple burrows and potentially multiple gophers. If you've ever walked across a landscape with gophers after the snow, you'll also see the imprint of their subsurface burrows. Gophers not only imprint landscapes at a local scale, but at a landscape scale as well. For example, in this Mima Mounds Natural Area Preserve of Washington State, these large mounds, Mima Mounds, result from the continued gopher bioturbation processes over hundreds of years, maybe even across a millennia. If you were to visit this area before this was scientifically known, then you may think that it was formed by aliens. Worms are also very important bioturbators, and Darwin wrote a treatise on earthworms and an ode to earthworms. This was his final book, and though today it's the least famous of his writings, at the time it was his best-sold book. Earthworms play a critical role in downslope movement, literally eating and passing soils. Through this, they aerate soils and decompose organic matter and bury organic matter. They're nature's plow, but one that results in sustainable changes in a soil. Of worms, Darwin said, "It may be doubted if there are any other animals which have played such an important part in the history of the world as these lowly organized creatures." Rain splash results in the transportation of sediment through the sudden impact of water droplets. This occurs when there's unconsolidated sediment at the surface. Once again, rain splash contributes to soil heave and downslope transport. And here in this image, you can see micropits that occur due to rain splash. At this micro scale, small parts are protected by coarse quartz grains at the surface. The imprint of creep is different with slope. Here, if we expand this system, we see this expansion and contraction that happens of the surface, a heave process. However, if we go down slope to a downslope position, we can see that the same agent doing the same magnitude of work, and that the blue arrows are the same size, results in further transport, even for the single heave event. So the steeper a system, the greater its transport capacity. So slope form controls soil properties, erosion processes, and erosion rates, and these in turn influence slope form. Picture a hill slope in the past, where we have creeping soil within a discrete layer. Let's step forward in time and watch as that land surface erodes. Now we have a past surface, the gray arrow, and the present surface, this black arrow. The material that's within that hatched gray area has eroded. And during the time that that material was eroded, each position on the hill had to be able to transport the material that was upslope of it. This means that point 1 only moved the material between the crest and point 1 past it, while point 2, on the other hand, had to transport a much larger amount of material, and point 3 had to transport even more. If steepness controls how much material can move and be transported, then a hill slope can't look like this if there's uniform erosion, as I showed. Instead, the hill slope would have to increase down slope. So that this is what the hill slope would have to look like in order to have a uniform erosion rate. Slopes have to increase downslope to accommodate increasing sediment transport downslope. So now you know why hills are convex. Process meets form on very different creeping landscapes.